previously we saw that when you induced a current through a conductor, you generated a voltage, an EMF, an electromotive force, and that was given by the electromotive force equals the velocity times the magnetic field times the length that you're moving the charge through. So what we're going to do now is some examples. The first example here is an induced EMF of a rectangular loop. So I just described the diagram. We've got a loop here, and you can see that it's moving up and it's making an angle of theta there between the x-axis and the loop. In the z-axis here, which I've shown going up the page, is the magnetic field B. The loop is revolving round. The length of this is B and the length across there is A. Using the cross product we can find out where the force is. So in this case we can see that if we put our fingers in the direction of the magnetic field and the thumb in the direction of particle, we can see that the force is being pushed that way. So we'll find that the EMF is in that direction. The rectangular loop of length A and width B is rotating with a uniform angular velocity omega, so that's radians per second, about the y-axis. The entire loop lies in a uniform constant magnetic field B, parallel to the z-axis, which is that going up. We wish to calculate the induced EMF in the loop using equation E equals VBL, so I've written it down here as E equals V sine theta BL. Along here and along here, as I said, you crossing V with B, you can see that the EMF is in that direction, and when you come all the way around, obviously it's now in the opposite direction, it's going round, so you can see that there's an EMF going that way and an EMF going this way. The motional EMF on each side of length A is the EMF equals VB sine theta A, so we got A there, and then on the other side, of course, it's the same again. Magnetic forces on the other two sides don't contribute because they're transverse to these sides. So that's basically what we've got for the EMF. For the total EMF for this loop then is given by this. Another way to get to here is to realise that the EMF is given by the integral of the velocity vector cross with the magnetic field vector dot dl. You know that V cross B equals VB sine theta, and you know that V is WB2, so you just plug those back in, and so the line integral around the loop reduces to two of those, so we know what this integral is. It's 2 WB over 2 B sine theta A. The 2's cancel here, so we get BA again, so we get what we had again. You can see that from the integral. So the product AB equals the area of the loop, so AB is this whole area. You end up with E equals WAB sine WT. We can also see that the maximum obviously is going to be when angle here is 90 degrees. You're going to get a maximum of WAB. You can define the maximum as Emax, and so you can rewrite, so here I've defined it as Emax, so we can rewrite this number 5 as this equation. So we end up finally with this equation that the EMF induced by this rotating loop is simply the Emax, which is omega times the area times the magnetic field B, sine WT. So EMF is related to this sine function. So that's the induced EMF of a rectangular loop.